Good morning, everyone. I am Dr. Senthilkumar, Professor in EC Department, TSB Engineering College, Karur. Today, I am going to talk about some fundamental topics on digital principles and system design. Of course, this is the course that we are going to see in coming classes. So, in digital principles and system design, there are 5 units. Now we are going to see the overview on Unit 1. The topic of Unit 1 is logic gates and minimization technique. Now we will see what we want to learn from Unit 1. The Unit 1 heading is again logic gates and minimization techniques. In that, we are going to see the following topics: basic theorems, properties of Boolean algebra, canonical forms and standard forms, digital logic gates, minimization techniques in K-map. Normally, K-map is nothing but Karnaugh map. Normally, it is used for up to 4 input variables and don't have conditions, NAND and NOR implementation. The following textbooks and reference books are prescribed by the syllabus. The students are requested to make note of these textbook and reference books for further studies. So next we see course objective. Upon the successful of completion of this course, the students will be able to facilitate understanding of logic gates and minimization technique to guide design of simple combinational logic circuits, to instruct on operation of sequential logic circuit, to demonstrate the basic architecture of computer organization, to explain the principle of parallel processing and memory hierarchy. The course outcomes are: it is expected from the students to apply Boolean algebra theorems and use simplification techniques, to understand the designing and implementation of combinational circuits, to understand the designing and implementation of sequential circuits, to understand the design of simple basic computer using registers and instruction codes, to apply the pipeline methods and memory hierarchy for performance computing. As I told already, since we are in Unit 1, where we are going to talk about some basic gates and minimization techniques, we have to concentrate on first line of course objective here, present, to facilitate understanding of logic gates and minimization techniques in course objective, and in course outcome, what we have to have is at the end of the session, you must be able to apply Boolean algebra theorems and use them for simplification technique. So this is highlighted here. Now come to program outcomes. This is normally prescribed by National Board of Accreditation. In that there are 12 program outcomes are expected. The first one is engineering knowledge, and then further program analysis, design and development of solutions, conduct investigation of complex problems, modern tool usage, engineer and society, environment and sustainability, ethics, individual and teamwork, communication, project management and finance, lifelong learning. So like this, there are 12 program outcomes are there. Now already we have discussed about what is course outcome and what is program outcome, and PSO, program specific outcomes are designed by our own requirement, our own discipline. Okay, so this is the COPO mapping diagram. So here what you have to understand is the numbering how we have given here. 3 in the sense it is meant for highly mapped, 2 in the sense it is meant for medium mapping, and 1 meant for it is low mapping. Okay. So some of the areas it is put hyphen here. It means there is no correlation between the prescribed or the desired CO and particular CO. For that, in the future, we will conduct some bridge topic. So to cope up with this correlation areas. So now we are in unit 1 consideration. In that, this COPO mapping, the first row is particularly meant for the first unit. These ideas that we have to discuss now. Now come to the main topic called Boolean Algebra and Digital Logic Fundamentals. So in that we are going to see the following subtopics. First one is Boolean theorems, canonical forms, and then logic gates. We will see K-map and NAND NOR logic. So this is the ultimate learning objective. At the end of the session, you will be able to understand what is Boolean theorem, what is logic gates, and what is don't care conditions, how it can be used, then canonical forms, K-map minimization techniques, and finally universal gates like NAND and NOR. Now come to Boolean algebra basics. The first one is what you have to understand is what is binary values. Normally, zeros and ones are involved in binary values. So, 0 can be considered as false or low, 1 can be considered as true or high. Okay, this matches the physical on-off states of transistor. Then primary operations, these are and or not. These three are called primary operations or primary operators involved in Boolean algebra. So look at operator precedence. So unless grouped by the parentheses, the operation are evaluated in the specific order. First you have to deal with not operation, then and operation, and finally or operation. Duality principle. So every algebraic identity remains valid if interchanging or plus or and interchanging 0 and 1. The examples are given here. So by seeing this example easily you can understand what is the duality principle. Here look at here a plus 0. Here plus is nothing but or operator is equal to a becomes valid. Look at here this plus is changed to dot, that is and operator. Okay, then 0 is changed to 1. It is the complement. 0's complement is 1, 1 complement is 0. If you interchange these symbols along with these binary values, then it holds the equality. So this is called duality. Now come to the verification method. There are so many verification methods are available. Okay. So as per syllabus, we want to see K-map variable minimization technique. Okay. So what are the things are available here under verification methods are first we have to have a truth table. Then we have to think about exhaustive use of inputs wherein the truth table has to have all possible inputs, and with the help of truth table we have to do algebraic manipulation. Manipulation in the sense we want to reduce the number of terms so that we can have a efficient digital logic circuits. Uh, We will see one by one in the few next slides. Now come to basic properties. These are all the properties available in Boolean algebra. First one is identity, next one is null, idempotent, complements, involution. So next is structure and order. In that case, there are commutative, associative, distributive laws are available. In the advanced reduction methods, absorption, consensus, De Morgan's theorems are available. Okay, we will see one by one. Now look at here. What is identity loss? Identity loss. A plus 0 is equal to A dot 1 is equal to A. This is identity law. Identity law. Next one is null law. A plus 1 is equal to 1. A dot 0 is equal to 0. Okay, as we discussed already, look here. The examples are given. Okay. Now, idempotent. A plus A is equal to A dot A is equal to a complement. A plus A bar is equal to 1, A dot A bar is equal to 0. The involution, this is 2 times inversion, A bar is nothing but inversion. Again, if you do another inversion on the A bar, then you can get A as a result. So, these are all the some laws involved in Boolean algebra. Now come to commutative laws and associative laws. Look at here. A plus B is equal to B plus A and A dot B is equal to B dot A. And in case of associative laws, it is A plus B plus C is equal to A plus B plus C. Look at the parenthesis, how it has been marked. And A dot B dot C is equal to A dot, in parenthesis, you can rearrange as D dot C. Now, this is about the distributive law, this is about absorption law. So, in distributive law, A dot in parenthesis B plus C is equal to AB plus AC, and A plus in parenthesis B dot C is equal to in parenthesis A plus B dot in parenthesis A plus C. Now, in absorption law, look at this. A plus A dot B is equal to A dot A plus B is equal to A. This is called absorption law. Now, come to De Morgan's theorem. This is one of the very important theorem. Mainly, it is used for simplification purpose. With the help of De Morgan's theorem, you can simplify the Boolean function so that you can have a efficient and simplified logic diagrams in digital systems. So these are the theorems normally involved. A dot B bar whole bar is equal to A bar plus B bar, and A plus B whole bar is equal to A bar dot T bar. So this is OR operator, this is AND operator. Okay. So here the simplification example is given. Look at the steps involved to simplify by using De Morgan's theorem. Okay. So look at here. A dot C go whole bar is simplified into B bar plus C bar as per this law and theorem. And finally, you can rearrange the literals to have a final terms like this. It is based on distributive theorem as it is given here. A bar dot B bar and plus A bar dot C bar. Now come to canonical and standard forms. It is involved with min terms and max terms. We will see in future one by one. Now you should understand that there are two terms called min terms and max terms. Min term is nothing but product terms, max term is nothing but sum term. With these ideas, you can have the standard form or canonical form. Okay. So look at the minterms, canonical SOP, sum of product. SOP in the sense it is called sum of product. Canonical in the sense it is product of sum. Okay. So in case of SOP, we are using minterms. In the case of POS, we are using max terms. Look at the symbols. The sigma is normally involved here. Here, pi-like symbols are involved to talk about the max term. Okay. SOP, sum of product can be like this. Look at this. This is the product term. Okay. Wherever you see the dot, that is called the product term. Wherever you see plus, that is called an odd term or sum term. Okay. Similarly, here in the case of POS, look how it has been considered. Here in the parenthesis, they have used sum term. Here also some terms are there. These two are coupled with and term. Okay. So it is product term. Okay. So you can call it as product of sum. So comparison and usage canonical unique for every function used for truth table mapping and analysis. Standard form often minimized form. Okay. Anyway, we are going to use some minimization technique. What we are getting at the end of the minimization in the forms or functions called standard form. When it comes, I will give you the detailed examples, illustration there. Now look at the min-term and max terms, how it could be. Here the illustration is given for three variable truth table. Normally A, B, C is called inputs. Okay. So with these inputs, there are 8 possible combinations of binary values could be like this. Look at this. In the case of decimal 0, the equivalent binary values are 000. Equivalent decimal 1, the binary equivalent values are 001. Like this, it goes and at the 7, for 7, decimal number 7, the binary values being like this. Okay. So the expected minterms for the corresponding binary numbers is like this. Look at this. Wherever, in case of minterms, wherever you see 0 and it is considered as a bar, because this term the relevant input is a. Since there is 0, then you can see a bar. So next also there is 0, then b bar. Next also 0, so c bar. Look at when you get without bar literally. So when there is a 1, so here there are two zeros, so a bar, b bar. Since it is 1 here, the corresponding c becomes c only. Okay. The corresponding input C. So it is taken as it is. So look at here, there are three ones. Here it is A dot B dot C. For min terms, the look at the operations operator used here. It is dot and product. Okay. Now come to the mass term. So what you have to understand is for each possible combination of input, you can have min term or mass or and mass term also. Look at the symbolic representation. Normally, min terms are illustrated with small m, max terms are illustrated with capital M. So it is A plus B plus C. Look here, when in case of unlike min term, in max term, wherever you have A, okay, with 0, it is marked as it is. When there is 1, it is complemented. The corresponding input is complemented. Look at here. Here if 1, the corresponding literal input literal is taken as it is, here it is complemented. And here it is dot and operator, here it is plus or operator. So this way the minterm maxims are constructed. Here for illustration purpose, they have used three variable truth table. The same thing can be happen for single variable, two variable as well as four variable also. As we told already, the KMAP can be used for normally four variables. Okay. So look at this. They have highlighted the row For decimal number 5, 101, see how the midterms are formed for 5 and how max terms are formed for 5. It is given here. Now come to how the SOPs and POS functions are formed. See, in case of canonical SOP, sum of product, look how they are using the truth table effectively. Now look at here. See, F here A, B, C's are input, F is the function output. Normally, to form the canonical form, you have to look at the output. Look here, it is 0, but 1 is available. The 1 corresponding to the row 1, another one is corresponding to row 2, another one is corresponding to row 3. But see the relevant minterms. Okay, SOPs are formed with the minterms. So here, if one is available here, the corresponding row 1 should be taken here, M1. If one is here, another one, and the corresponding row is M2. If one is here, M3. All other outputs are 0, so it is omitted. So the corresponding M1 values is already we discussed in the last slide. Okay, if M1 is there, okay, it should be taken as A bar, B bar, C plus M. For M2, it is A bar, B. Since 1 is there, we have to take B as it is, and since it is 0, C bar. Likewise for M3. Now come to the canonical form for POS. It is being like this. Okay. So here you have to consider zeros. Here zeros relevant to row 0. Here 0, 4, 0 is 5. Here it is 6. So M naught dot. Here it is plus. Here you have to take dot to form POS, product of sum. Okay. Dot, dot, dot. Since 1, 2, 3, 4. In 7 also there, 1, 1, 1. Here it might be 0. So that is also taken. Here M7. Okay. So here it could be max term, it is 0. So that is also taken. Now this is the function without any simplification. Okay. Now you can do the simplification by using Boolean algebra. See, they have given the example with the help with the idea of canonical SOP. With the help of Boolean algebra, they have simplified the function. For this function, it is simplified by using Boolean algebra, and the final function f is equal to a bar b plus a bar c. So it can be called as the final function can be called as a standard SOP function. Now come to the digital logic gates. There are so many gates are available. With the help of these gates, the implementation, final circuit implementation, digital circuits are constructed. Okay. So AND gate, look at the operator, what they have used here. A and B's are inputs. Okay. So the output condition is all output becomes 1 only if all inputs are 1 for the AND operation. For OR, the symbol used is plus. The output condition is the output becomes 1 if one any input is 1. Not it is the inverter. Look at the symbol A. If A is the input, the output could be A bar or A dash. Inversion output. If input A is 0, A bar is 1. If A is 1, A bar is 0. And NAND, it is another operator, NOR also the another operator. These are all called universal operators, and followed by not. Okay, look at here A dot B, and along with if the bar is there to talk about a not, then it becomes an AND. From AND you can take NAND. Similarly from OR, if you put the bar, so putting parentheses and bar, then it becomes NOR. Then XOR gate will be like this. The symbolic representation is like this. Look at the condition for output. Output 1 if inputs are different only. XNOR, and the symbol should be like this, dot with circle. And the output condition is output 1 if inputs are same. Otherwise 0. That is the meaning of it. Okay. Now come to the symbolic representation of basic gates. Here three gates are given. One is AND gate, another one is OR gate, another one is NOT gate. As you see here, these are all two input gates. Okay, A and B's are input, Y becomes output. Look at this. So the for two inputs, there are possible combinations, four possible combinations for all the gates. But here, since it is the NOT gate, only one input. When there is A in the input, output should be A bar, that is equal to Y. Look at here. So accordingly, for all, if there are two inputs, the four possible combinations are like this. As we discussed in the last case for the output condition, when both inputs are 1, the output becomes 1. Otherwise, it is 0. For OR gate, if at least one input is 1, the output is 0, 1. Okay. Otherwise, if all inputs are 0, the output becomes 0. So this is illustrated here. Okay. For NOT gate, if input is 0, output is 1. If input is 1, output is 0. So this is the condition. So y is equal to a dot b, the function, final function you can see. Look at here. Here there is only one, so 1. So here there are three ones. There is a simplification procedure available that we will see in the remaining coming slides. Now you should understand for our operation after simplification, y is equal to a plus b. This is the final function for OR gate. So this is final function for NOT gate. Now look at here, with the help of AND you can implement NAND. Without this bar it is AND. If bar is there, then it becomes NAND. Now in the AND gate here, look at here. Here only you had one. Now since we are flipping, that is with the help of inversion, and we are flipping the output. Okay, here wherever you see previously 1, it becomes 0. Wherever you had a 0 in previous AND gate, it becomes 1. Similar case for NOR gate also. Earlier stages, here it was 0. Only for NOR operation, here for this combination, here it was 0. Now it becomes 1 with the bar. And the remaining things were 1 in the previous case without bar for R. Now it becomes 0. Okay. So this you have to understand. So here some of the implementation strategies are given as example. Okay. So look at this. A NAND A becomes A bar. It will act as NAND gate. It can be act as a simple NOT gate. In the coming slide, I show you how it working. We'll see. See now. Look at here. Dot plus dot. Now, if you put the bar along this, see this can be replaced. Okay. How these operators are effectively used for the equivalent implementation of logic function, you can see here. Similarly, look at here. Actually, here there is a dot symbol. Okay, and operation. And this operator is replaced with OR operator when you put a bar. So these two are equal. Okay. This will be equal to this. This will be equal to this. By simply changing the operator along with bar, you can make an equal function. That is the conclusion here, called conversion logic. Now come to XOR and XNOR gates. Okay. So look at the symbol, how it has been used. These symbols are very much important. Okay. So again, it is a two input XOR gate. This is two input XNOR gate. Okay. So if inputs are equal, A is 0, B is 0 for XOR, okay, it is 0, XOR it is 1. Look at here in this case. If both inputs are 1, here it is 0, here it is 1. Okay. If different inputs are there in each combinations, for XR it is 1, XNOR it is 0. Normally you see here XR is inversion of XNOR, or else XNOR is the inversion of XR. Look, if wherever you see 0 here, the corresponding value here is 1. If it is 1, it is 0. If it is 1, it is 0. If it is 0, here 1. So these two are inversion equality. Okay. Here it is 0 in the sense, here it will be 1. If here it is 1, here it will be 0. So look at the symbol, look at the operator, and how the algebraic functions are used here, that you can see. Here a bar b plus a b bar, here a b plus a bar b bar. Okay. So some of the common uses are given here. It can be used as parity generator, can be used for comparator, can be used for adder subtractor, can be used for encryption techniques. So these are all the major application of XOR and XNOR gates. Now come to K-map. So this is used for a three variable K-map. Look at the structure, how it has been used. We will see some detailed simplification procedures in coming classes. Now we see how the structure is given for K-map and how it can be simplified. Okay. Now the basic concepts behind the K-map simplifications are these things. First one is powers of two. Groups. You can group the after framing the K-map table. You try to group the available ones so that you can think about the simplification procedures. So the grouping can be like this. Group must contain 1, 2, 4, 8, 16 cells. Okay. So likewise only you can combine. Here 4 grouping is given. 4 number of zeros has been grouped, and 4 ones can be done as a group for simplification. See, requirement is maximize the group size. If 16 cells are possible to combine, then you should combine all 16 cells at a time. Instead of combining, you should not go for a reduced number of terms. Either you should not use 2 or 4, 8. So you must be able to cover maximum group size. In that, all ones must be covered. Next one is wrapping around adjacency. Example is like this. If here ones are available at the edges, it can be grouped. Okay. So that is called the wrap around adjacency. So essential groups, in the each group at least one uncovered one must be covered. That is the requirement. So this is the structure for K-map structure for two variable K-map. This is the structure for three variable K-map. Okay. So it could be like this. Look at how the placements are given. This is the place for, in the case of two variable map, this is the place for M0, this is the place for M1, M2, M3. Here in three variable K-map, the structure could be like this. There should be 8 boxes in K-map, square boxes. This is for M0, M1, look at here, M2 comes here, M3 will be here, M4, M5, M6, then comes M7. So this is particularly arranged like that so that you can have a systemized simplification procedure for K-map. Okay. See, the very important point is if it occupies, these ones come from the output. Okay. Wherever you see the output, these ones will occupy. Okay. It seems here all squares are occupied with 1. So all output is 1. So if it is being like this, you can cover up all the ones so that you will have a function as 1. Here how it comes, see, in the sense, look at here, there are 4 ones here, you can combine 4 ones like in whole. Instead of covering 2 ones in 2 steps, you can cover all the 4 ones at a time. If you cover all the ones, this 2 will get cancelled because in this side there are 1 1, so it will be cancelled. In the horizontal side you see here 0 1, that is B get cancelled. If in the C here is 1, here is 1, so 1 meant for C in SOP form, so C will come. So this way is try to simplify. So this is the minimized expression. 4 variable K map without don't care. Okay. In the previous cases, we had K maps. See, in these cases, each cell will be occupied by either 0 or 1. But in some cases, the don't care states can be effectively used. Normally, these don't care states are marked with the X. You should understand what is don't care. Okay, an input combination that never occurs or whether the output does not matter. We can treat X. X can be either can be treated as either 1 or 0. Okay, so what is the use? It can be used effectively to have a grouping so that you can use it for simplification, effective simplification. Okay, look at here in this example, 4 variable came up with don't cast. If you are not considering these don't cast, so you can have a simplification with ones. Okay, here, here, this one. Okay, with the help of these 4 ones, you can have a function, simplified function, but you can reduce only 2 literals. Okay, when you consider x also, now you can group. See, in the previous case, you had only group of 4. 1, 2, 3, 4. Now, x also is considered for grouping combinations. Here 8 comes. So, among the 4 literals, 3 will be dropped out. Finally, you will have B bar as the output. Okay, in this case, okay. So in this case, see, in this row, all the ones are available. So it will go out. This term will go out. Here also, all ones are available. This term will go out. Okay. Look at this. So finally, you will have 0 here. Finally, you will have 0. Here A bar, B bar plus A, B bar. In that, A bar will go up, only this 0 will come out. So this since it is 0, the B bar will come in, okay, as the final simplified expression. So this is the advantage of K-map simplification procedure. The previous case, without x also you can combine, but in this particular case, if you use x effectively, that is don't care state effectively, you can reduce the number of literals in the output function. Cut this how again you will have simply one literal in the output. Now come to NAND and NOR implementation. So how NAND is effectively used, you can see here. If F is equal to A bar B plus CD bar can be converted into AB dot CD. This already we discussed with the bar. Okay. If you change this operator, you can put bar, so it will be equal. Similarly, look at this. This is A plus B dot C plus D. Since this dot is replaced with the plus, it can be rearranged with the complement symbol like this or inversion symbol like this. Okay. So with this, you can have a different NAND and NOR implementation. You will see how it can come. Look at here, AB is AND operation, this is OR operation, this is AND operation. Now you can consider this is the whole thing, this is whole thing, now dot is there. So if you see dot, it is AND, if along with the bar it is NAND operation. Now plus is OR, already these two are plus OR operation. So if you combine these two terms along with this plus and this inversion complement function, then it becomes NOR operation. Okay. So this way, the function can be rearranged. Any given function can be rearranged in the form of either NAND and NOR, so that you can have a universal gates in the final implementation. Okay. So look at this, some of the examples I have given, how OR logic is effectively used with the help of and NOT. Okay. So this is AND operation. Okay. This is OR operation. See here, AND operator is converted into OR operator with the idea of this logic, not operation. Okay. See, OR logic is this one. Wherever you see plus, it is OR logic. Now look at here. This is AND operation. These three are not operation. This AND operation can be converted into OR operation with the help of NOT gates. Okay. Similarly, this is OR operation. So this is OR operation. This OR can be converted into AND with the help of these NOT gates. Okay, so this is the logic. You have to understand how AND can be converted into OR, how OR can be converted into AND operation. So look at here. As I told already, NAND and NOR gates are universal gates. With the help of universal gates, either NAND gate or NOR gate, you can implement any function. So these are the illustration how the different functions are implemented with NAND gates. So this is to talk about not in gate. Okay, this is A dot B AND gate, OR gate, NOR gate again. Okay, so look at this how NOT gate is implemented. If two inputs are combined together and a single input is given to that, it becomes NOT gate. A plus B is converted into A plus B bar, full bar. Okay. So look at this. This is the symbol NOT gate. So if this one input is connected to another input and converted into single input, it provides NOT output. Okay. So buffer in the sense that the same output will come out. With the single two inverter, you can have a buffer. So this is the example for exclusive OR. This is for exclusive NOT. Okay. So by this, I request the students to identify NOR gate symbol and do some conversion process to implement all other gates with the NOR gates. So now we come to the end of the session, summary and next step. So in the summary, we covered the following topics: Boolean algebra and laws, canonical and standard forms, basic logic gates like AND or NOT, and at the end we discussed about an AND NOR gates also. In K-map simplification procedure, we have seen how the tables to be constructed for two variable, three variable, four variable maps with the help of min terms, max terms, and the relevant functions. Okay, we have shown some of the implementation by using NAND gates. I left NOR gates to the user or students to do as the homework to find different gates. So this is the practice for this session. Try to form different truth table for different functions. Then do the find the canonical form of SOP POS forms. And if possible, you try to apply Boolean algebra to find the simplified standard functions also. Finally, the design challenge, you can think about K-map simplification procedures, and after finding the simplified function, you can go with only NAND gate or only NOR gate to implement the function. Keep in mind, without a NAND NOR also, by using basic gates, you can implement the final standard simplified function. But sometimes in the question paper, they may give like this. use only NAND gate, use now only NOR gate, like that. I request the students to practice for all type of implementation procedures. Okay. The advanced study topics for this session is they can talk about hazards, and some other simplification procedures are available apart from K-map, called the Queen-Mahalski method or tabular method. I suggest the student to go through these topics also as the advanced topics. And there are some multi-level logic optimization techniques are available. These are all the topics the students has to study further.